Okay, welcome to Digital Logic Part 1. So we finished up the first block of the course and we're going to move on to this next section, which is digital circuits. This lesson will be on some of the basics of digital numbers and digital logic devices. So why are we doing this? Well, this asks a rhetorical question, which is real. Of course, this continuous data here is real world stuff. So we think about, what could this represent? It could be measurements from a sensor, it could be temperature, it could be speed, maybe it's force changing over time, etc. Those sorts of things. Those quantities vary continuously. They don't vary in discrete changes like we do with the digital signal. So why do we deal with digital? Well, of course, because the devices that we're using, microcontrollers or computers, can only really work in the digital environment. So these sorts of analog signals need to be able to be represented digitally. And the techniques we're going to talk about today are how we do that. What are, let's see, here quickly, a little digital joke. So, oops, too big, too zoomed in. Okay, so today we're going to talk about digital combinational logic, which is different from what we'll do next time, which is a little bit of sequential logic. So digits represent the state of the system. So that could mean, in the simplest form, something is on or off, or we also might say true or false, high, low, etc. And we've dealt with that a little bit in our labs. And with digital logic, we make decisions based on the state of something. So here's an example where an aircraft may be thinking about whether or not it's safe to release a weapon, and that's a function of, that's what this F of means, function of aircraft speed, the weight on the wheel switch, the G's that it's experiencing at that moment, the door position if it's an internally carried weapon, etc. And then the output would be determined by all of those inputs. In this case, when we're talking about combinational logic, we aren't concerned with timing at this point. We're only looking at whether or not the inputs are at a certain state. Okay, so for any given system, there may be some indeterminate number of inputs. They're usually, if we're looking at electrical devices, they're either at 0 volts or 5 volts. We'll talk a little bit more about that. And that's going to create some output. And there are definitely lots of ways to solve these types of problems. So down here are some sketches of some very simple devices. So in this case, we see we have 2 push buttons in series with a lamp. In order for the lamp to get power, button A needs to be pressed and button B needs to be pressed. So that is clearly an AND device. Over here, there's path for current to flow through either button A or through button B. And either way, the light would light up. So this is clearly an OR gate. Okay, so we might ask ourselves, why are we, I'm going to jump back to here, why do we want to use digital? Or what are some differences between the two? So for analog signals, their benefit is that they represent real world information. They can also provide higher resolution than a digital signal because it's true information. So as long as you have the ability to detect down to a small level, you can get much higher resolution. Now, those are benefits, so I'll use a plus sign here. Disadvantages of using analog signals that they require much more memory. And they are more susceptible to noise. What's noise? Well, noise is anything that is not part of the original signal. So in real world measurements, you usually get some kind of interference and your signal actually looks like this. It's not a nice, pure, clean line. If it looked like this, it'd mean it'd been filtered heavily to get that. So when you're really measuring real world information, it's going to come with some extraneous information that wasn't part of the quantity you're actually trying to measure, and that's noise. So noise is a problem. We'll talk about that a lot more when we get to sensors in a few lessons. So benefits of digital. We look at digital. It's faster to process. It is. I'm gonna start writing up here because I'm gonna run out of space. It's easy to store, and it's easy to transmit, to communicate. Uses less memory, so lower memory, and these are benefits. It's less susceptible to noise. You could say it's robust to noise, susceptible to noise. Keep wanting to spell noise with a C. And it's perfectly replicable. Or digital signal, it's much easier to reproduce. Now, the major drawback is that it is lower resolution. The fact that it's lower resolution leads to it being less memory to store, easier to transmit, to communicate, etc. Okay, so moving on here. In class, we'll do some board work exercises. We'll go through these in a little worksheet and see how to do some of this arithmetic. But we're going to need to know how to do these different things, understand the differences between decimal numbers, binary numbers, hexadecimal, how to convert between them, how to do some simple arithmetic, so adding, subtracting in those number bases. Here quickly, we'll also do look at some different logic devices and how they work. I want to point out real quickly, there's some really cool online logic gate simulators, and so I'll pop these down here real quick. This is one called logic.ly or logically. So this is cool. I just built this simple circuit. This is, well, let's see, what type of device is this? We can test it. So these are toggle switches, and these are lights. If I turn on this switch, so right now these switches are off, and the light is lit up. If I flip that switch to turn on the switch, the light is still lit. If I turn on the second one, the light goes off. So that is a NAND gate. That's this guy over here. So it only operates when, or it turns the light on unless both switches are flipped in the AND condition. Okay, so that's one example. And you can build different things. You take this and you drag it on here, and then you can have different outputs. This will get much more helpful when we get to more complicated devices like these flip-flops in the next lesson. Another version is this is at sciencedemos.org. Here's another one I built. In this case, you click on one of these things and then place it on there. And that's how you use that. Just gonna delete that. I tried to delete it. Anyway, here's a simple circuit I made with two push buttons. If we push that button, the light turns on. If I push this button, the light turns on. So I can push the first button or the second button. So this is an OR gate. Okay, so get that out of the way. So those are some fun things you can check out if you'd like. Okay, these are basic combinational logic devices. So these are the different devices. In the class, we'll fill out a table for how these work. So this is a simple buffer, meaning it does not change the state. So C, the output, equals the input. The next one is an inverter. It changes the state from the previous state, so it just does the opposite. So this over here is called a truth table. You've probably seen these before. With a truth table, we list the inputs first, and then we list the corresponding output. Okay, so an AND gate, very simple. Both inputs have to be true for the output to be true. And this is mathematically how we describe that with the dot symbol. So here, I always like to distinguish the inputs from the outputs clearly. These are the two possible inputs, A and B, and they result in an output. And we see that the output is only true when both A and B are true. Now, one thing I want to show you here and point out, and I ask you to do this, it's best when you're filling out a truth table like this to count in binary. So meaning this starts with 0, 0, which is 0 in binary, then 0, 1, then 1, 0, then 1, 1. Okay, and then we'll see another example of that in a second. So these are the different types of logic gates. You should study those and know how they work. Okay, one important point here is we're going to actually implement these in digital devices. And one of the first things you'll do in the next lab is test when your Mega thinks an input is high or low, and it actually changes depending on if you're switching from high to low or low to high. So that's a really important thing to understand. So here, what we're pointing out is that with different types of devices, those points where we flip from being low to high changes depending on the type of device. So for a TTL device, it will treat any voltage that's below 0.8 volts as being quote unquote low or false, and anything above about 2 volts as being high. And then it will try to output a voltage that is less than 0.5 volts if it's low, or greater than 2.7 volts if it's high. Now, if we're using a CMOS device, a complementary metal oxide semiconductor, which is what MOSFETs are using, your tolerances, if you will, are much tighter. So it needs to have a voltage that's less than 1.5 volts or greater than 3.5 volts. What happens if you're in between those? Well, that's an undetermined state, and we don't really know. And it will probably just remain where it was before. So if it was high before and it's getting lower, lower, lower down to like 1.7, 1.6 volts, it's going to stay as high until it gets below this 1.5. Okay. And then on the output, it will clean it up. This is what's so nice about using digital numbers and digital information, is that even if your input, so they say this is your logic device, and going in, you've got a voltage of 3.7, it will output a voltage that's 4.95 or better. So it's going to improve the quality of your signal just by passing through the device. This is one of those things that if you're doing a real world system and trying to build something, just be careful and make sure you read the data sheets on those devices so you understand where those thresholds are. Those will be clearly listed on the data sheet. Okay, let's do an example of a logic device. So here's an example for a simple car alarm system. So you can imagine a car alarm. It probably has different sensors on it, and you want it to turn on the alarm when it thinks that something nefarious has happened. Someone's trying to break into your car. So if you think about the simplest type of device, a car alarm, you would want it to be armed when the owner sets it into security mode. So they lock the doors, push your button on your key fob, and it triggers the device, or arms the device. Then at that point, should anyone open the door, you would want the alarm to go off. The other time you'd want the alarm to go off is if the owner pushes the panic button on the key fob. And you would want that to go off regardless of whether the system was armed or not. Anytime that panic button is pushed, you want the alarm to go off. Okay, so anyway, these kind of outline how this car alarm should work. So we have 3 inputs. We have the alarm state, that's whether or not we were armed, and it's armed when that state is 1. Okay, the panic button, which 1 means the panic button has been pushed, and then the door position, is the door open or is the door closed? Okay, so like I said, so over here, this is our truth table, and we're going to, these are our inputs right here, and then after that is the output. So again, we want to start by just counting in binary. So I'm just going down and counting in order in binary like that. That way, when counting in order in binary, it makes it easier for me to grade your work because all the inputs will be entered the same. That way, the outputs will be in an expected order here. Okay, so that's the first part. Now we want to go through a logic to figure out which states the alarm trips and fill those in this input column. Now, in this case, so one way to look at it is we want the alarm to trigger anytime the panic button is pressed. So I can go over here and just see anytime P is a 1, I want the alarm to go off. It doesn't matter what anything else is. So that kind of simplifies that. Now, another thing we could do is look at when the system is not armed. So when O is 0, we don't want the alarm to go off. The alarm should not go off, so those are zeros. Now we're just left with these two situations we have where the alarm is armed and then the panic button has not been pushed, and it's just a question of what is the door state. So if the door is open, we want it to go off, and if the door is not open, it should not go off. Okay, so there's our truth table figured out. So now we can create a Boolean logic expression based on this. So we look at all the cases in which the alarm is going off, or where the the output of this device is true. So those are all these situations. So I write that as this is not O. So we go not O and P and not D. That's the first one. And then or, so plus sign means or, so this is not O, P, not D. This is not O, P, D. This is O, not P, not D. This is O, P, not D, O, P, D. Okay, so we're going to just put all these together. D or O, P, not D, or O, P, D. Okay, now we go through some algebra to simplify this, and this would equal the alarm. There's some, I'm going to give you a handout class. There's also a table in the book that shows you how you can simplify some of these. We'll go through this really quickly here. So we can collect like terms. So we've got not O, P, and not D, or we have and D. So these can be combined like this. Right, so that's a simple one. We also over here now we have O, not D, with P or not P, or vice versa there. Or we're going to add, we're going to do something called, what's the idempotency rule, where this, we're going to take it and go, this can be the same, because we have this term here, we can just use it again. So we're going to have OP, not D, or OPD, and we're going to combine those to be OP and not D or D. And so that's what that's going to go right here. Okay, now what? Okay, so we can cancel all these out because these are just, we're saying that in either state, this is still true. So we end up with these guys, and then I'm going to collect some more terms here. So I've got a not O or O group with P, or I have O not D by itself. Okay, so that simplifies to just P because this cancels out P or O and not D. Okay, and then we want to just draw a circuit diagram of this. That's the last step. So we have an OR, so we can write an OR gate, and the output of that will be the alarm. And an input is P, and then we have, that's ORed with this guy, which is going to be an AND gate with O, and then we go D, and I'm going to put this into an inverter like that. And so that's one way to draw that alarm. Okay, so next slides were just, here's that example again, just in subsequent slides. Okay, so that's a simple way to create a device that can take multiple inputs and make a decision. So this is actually pretty cool. Now we have the ability to design devices that can make decisions, that can think logically. Okay, how would you actually implement this in circuitry? Well, there's these devices called integrated circuits, and we talked about that a little bit. Now we're gonna start using these big black things that are in your toolboxes. These are devices have many of these logic gates built into them. So one of these guys usually has 16 pins, 8 on each side. This one or could have 14 pins. So this device, CD4071, will use that class. It has a bunch of OR gates inside. It's got 4 OR gates. We need to provide it power and ground so that it's powered, and then it will take inputs in many different places and give you an output. Okay. So I'll show you how to use those in the lab, but they come in many different sizes, different versions. So the CD4081 is why are you saying pairing? Testing, testing. Okay, testing. Okay, hopefully you can hear this. I was using a Bluetooth headset and it dropped off. We're almost done here. So as I was saying, these integrated circuits come in many varieties, and they'll usually, in terms of digital logic gates, they'll have different types of gates. So we'll use AND gates, OR gates, we'll have inverters, and there's other more sophisticated devices that do other things as well. Here, I just want to briefly show you some interesting other logic circuits. So this device here is called a multiplexer. So how would we analyze this? Well, again, so it's got 3 inputs, a select, and then D0 and D1. These are all the inputs. And so again, we would fill out this truth table by doing our binary. And then let's go through and see what this looks like. So this is S naught. So that's this guy, the output right here. So that's just, it's not necessary to put this in here, but it's really nice way of showing your work and being able to just step through easily and not make mistakes. So this is just the opposite of S. So that's really easy to fill out. Then we see that O0, again, that's an intermediate output. That's this guy. This is the combination of D0 and S naught. So it's an AND gate. So this is going to be high whenever D0 is high and S naught is high. Well, that's happening here and nowhere else. So those are all zeros. So that's easy to figure out. And then O1 is a combination of select and D1. So that's this guy and these guys. So that's true in these cases when those are both high, and otherwise it's all 0. Okay, so then the output is an OR combination of those. So anytime O0 or O1 is high, we get a high on the output. Okay, so what is this thing doing? So this is the output. Well, we see that when the select button is low, it reproduces just the output of D1, or sorry, D0. And when the select button is pushed, it gives us D1. You see how those match right there. Okay, so this allows you to select from two inputs. You can either pick, I want to know what D0 is telling me, or I want to know what D1 is telling me, and you choose them by pushing the button or not pushing the button. And so that's a cool device that's fairly simple, one of the more straightforward devices. Okay? Of course, there are much more sophisticated devices, things that do arithmetic, that select from multiple devices, that count, do all kinds of cool things. So we'll see a bit of those later on. Okay, that's an example of that. Okay, there is a homework assignment. So it is in the Teams page in the folder. This is very similar to the car alarm that we just looked at, this guy. So you're going to read the scenario, fill out a truth table, write equations, and write a circuit to implement it. Okay, and this homework is going to be part of your pre-lab and the first thing that you do in your lab when we do lab 5. So it's leading up to that. This is a fun little problem, and will give you a chance to practice some of these. Next lesson, we're going to do what is called sequential logic. And with sequential logic, we care about time. And this is a plot showing this is the marching of time forward here. And so how do these devices work when we're giving them inputs that are varying with time? That's what we'll look at next time. Okay, thanks for your attention, and I'll see you in class.